Let's get All right, I guess I'm back. I don't know what happened there. I got bounced back. I'm on campus and the internet connection on campus is terrible. Okay, so I think what I was talking about was what was on the exam when I got booted out. So again, for the chapter on torsion, it's going to be angle of twist and the statically indeterminate problems, both that part. Then for the bending chapter, calculating shear and moment diagrams, both analytically and graphically. Also in that chapter, you have to be able to use the flexure formula, MC on I, to calculate the bending stresses, right? You need to be able to calculate I. So very often that's going to involve parallel axis theorem, right? So that material, that's actually in the appendix. And then in chapter 7, I believe, where we do transverse shear from bending, right? Again, they're using the transverse shear equation, tau equals VQ on IT, to calculate the shear induced from bending. Also, remember we did those problems where we looked at the shear flow to determine the spacing of fasteners, okay? And that'll be it. So it will not include anything on chapter 8, combined loading, okay? Which is what we talked about last class and we'll continue talking about today. Is there any questions on what will be on the material on the exam? It'll be very similar to the other exams, right? Pretty much homework-ish type problems, right? Okay. Well, if not, let's get started on today's material. So today, I wanted to talk about what is normally referred to as combined loading. Even though we talked about pressure vessel problems, they're kind of combined loading because you have multi-axial states of stress. But honestly, what we're going to talk about today really is combined loading. And in fact, there's really nothing to lecture on because it's all material that you've seen before. So let me just start with a fairly simple problem. So I think you can see the whiteboard thing. So imagine we've got a solid shaft here, right? This is circular, and let's give it an outer diameter of 3 inches, an inner diameter of 2 inches, right? So it's a hollow shaft. It's fixed at this back end. All right. And then, well, okay, let's give it a length. So it'll be 4 feet long. All right. And then welded onto the end is this extension arm, which is 1.5 feet. And at the end of this, we have a downforce applied of 1,000 pounds, okay? All right. And so let's put some coordinate axes here. So let's call this the positive X direction, this the positive Y direction, and then if it's a right-handed rule, up would be the positive Z direction. And let's talk about what is happening here at this back cross section, okay? All right. This is a very classic, pretty straightforward combined loading problem. You have the 1,000 pound force, right? So if we were to take that and relocate it right here into the middle, right? I'm going to relocate it with, I'm going to use blue for that, right? We would have 1,000 pounds acting down, but also we would have to add the moment arm that comes about from the fact that the 1,000 pounds acts at that 1.5 feet moment arm. And so that would be putting a torque here of 1,500 pound feet, okay? So these blue forces are equivalent to the 1,000 pound force applied at that tip, okay? So what I'm trying to illustrate here is that this offset 1,000 pound force produces a down force, this 1,000 pounds, that will give me bending. It's going to want to bend this hollow shaft down, but it also produces a torque and wants to put torsional stresses on here. So back here at this back plate, or really anywhere in this member, you're going to see stresses that arise both from bending due to this 1,000 pound force, MC on I stresses, and also torsional shear stresses from the 1,500 foot-pound torque. Those are going to be, remember, TC on J type of stresses, okay? So this is a classic combined loading problem. In fact, there is a laboratory set up in the Lockheed Martin lab that looks very similar to this, and I will post right up in there. We will get you the test date off of there, and we will do a little project based on that as well. Okay? But anyway, all right. So the problems will normally go like, if I were to zoom in on this cross section here, where this is the y-axis, this is the x-axis, and this is the z-axis. You might be asked to find stresses at various points on this cross section. Typically, it'll be like, noon, 3 o'clock, 6 o'clock, 9 o'clock, right? So let's call this, for lack of a better word, A, B, C, and D. All right. All right. So on this surface here, this entire cut surface, we have a bending moment and a torque applied from this 1,000 pound force, or I think from now on, I will just ignore this and we will just deal with the equivalent translated force and torque there, okay? All right. So what are the forces acting on this plane in the back that contains points A, B, C, and D? All right, well, clearly we have the 1,500 pound foot torque, right? So I have a torque acting on this like this of 1,500 pound feet, right? Okay. I have the 1,000 pound will put a shear force acting down, right? That's 1,000 pounds. Oh, let's just do this with an arrow. That would be the shear force that you would see in the shear diagram due to the beam. If we look down this like it were a beam now, right? This is the 4-foot length, or 48 inches, whatever you want to call it. I'll just, right? And we have 1,000 feet down here. I'm going to 1,000 pounds acting down. Then to balance that, we're going to have an upwards shear of 1,000 pounds, and as well a bending moment that's going to go in this direction of 4,000 pound feet. All right. And this cut face here is just on a little differential segment, just a little bit to the right of it, you know, the way we're looking at this. So that's why the force and is acting down, the shear force instead of acting up, right? So we're actually on this face here. Okay. And so, right, so we've got the shear force, we've got the torque, and we also have this bending moment. So that's going to be a bending moment around the y-axis. It's going to go like this. And that's the bending moment around the y-axis of 4,000 pound feet. Okay? All right. So those are the forces acting on that section. So that's always going to be our first step. Step one is going to be to find forces, moments, and well, torque is a moment, but I'll say torque. Oops. On the cross section, right? All right. And so that's what we have there. All right. Now, the next thing that you're going to want to do is they're going to ask you to calculate the stress state at a particular point. So, for example, let's say the problem were to ask us, what is the stress state at point B? Okay, so let's say that that is the problem. Well, at point B, if we were to kind of zoom on a little differential element there at point B, you got to imagine this is a very small cube of material that exists right here at point B, right? And again, still, this is the X direction, this is the Y direction, and this is the Z direction, right? So let's go one by one and look at the effect of each one of these forces on the cross section, right? The torque, the shear force, and the bending moment, and see what types of stresses that produces at point B. All right. So let's first talk about well, let's go in the order that we learned this stuff. Okay. So, so first we have the torque, right? So let's consider, oh, did I get kicked out again? What is going on here? Why is my share lost? Okay. All right, I'm still in the meeting, but somehow it decided to stop sharing. All right. Yeah, this. No, this is the wrong one. Where did it go? All right, okay, we're back. All right, so let's first consider, so step 2. We're gonna find
Professor, I think you're not sharing your screen.
Oh,
Yeah,
no?
yeah,
Okay.
sharing your screen.
Okay, nice. So we're going to find the stresses on the differential element due to each force, or I should say loading, okay, on the section, right? So first one we're going to do is the torque. And this is going to give us a torsional stress, tau equals TC on J. All right. All right. So, I already calculated this earlier so if you look at this geometry, right, and you calculate it, J turns out to be 6.38 inches to the fourth. I is half of that, which is 3.19 inches to the fourth. And the cross-sectional area is going to be 3.93. And that's inches squared, right? All right. So we know the torque is going to be the 1,500 pound-feet. We know C is the radius, the outer radius. So that's 1.5 inches. And J is the 3.19 inches to the fourth, right? So this is going to equal 1,500 pound-feet. And let's convert that into inches. So there's 12 inches per foot. All right. C is going to be the radius, the outer radius. That's 1.5 inches. And that's all over J, which is the it's the 6.38 inches to the fourth. All right. So what does that mean? Okay, so if we get that number. All right, that gives me a shear stress due to the torsion of 4.23 KSI, okay? All right, now we've done this all before, but now here's something we haven't really emphasized previously. What type of stress does that produce on this little differential element here at A, okay? So I don't know if you can still see my camera, right? So if here's the cross section, right? And up top is point B. Right, so there's point B. Now the torque on this face, I know it's hard to see, right? The torque on this face is going in the negative direction on the x-axis. So it's actually going this way, right? The torque is being applied on this face in this direction. So if I were to kind of draw that, right, it's coming around the x-axis. It's going on the negative axis. So the torque would be going in that direction, right? And if that's the case, the traction it's going to put on the face B is going to actually go to my left, your right, okay? And that's, if you want to think of it, that's acting on the front face at point B. So that's going to act, what's showing here on this disc is actually acting on this face. And so it's going to be a traction that goes like that. Does that make sense? That's what's acting on that cut face due to the torsion. Now, obviously, that's not the full state of stress, right? That has to be balanced with the typical shear stress type of couple, right? But that's what's acting on there. So the shear stress due to torsion, this one is really a shear stress acting in the XY plane, all right? And it's actually acting in this direction. So this here is the 4.23 KSI, okay? All right.
So, sorry, Professor.
Yeah, sure.
So that stress will be acting on the XY plane, but in the direction of the Y plane, because it looks like it.
Well, no, look, remember, so yeah, this is the really important part of this, right? So when I cut the cross section, right, this is what you see on the front face. Now we take a little differential block here at point B. That's what I've drawn here. So on this front face, yeah, the torque is giving me a shear stress in the Y direction, yeah. But on the back face of that cube, it would be in the opposite Y direction. But also in the side plane, which is going down the x-axis, right? You would see this shear traction, right? Shear stresses always act on a plane, you know?
And
So
is it the same?
when you draw a shear stress, that's not a shear stress. Shear stress looks like that. Does that make sense?
Yeah. And another thing is the 4.25 KSI stress going to be equal on all faces of the differential?
Yes.
Okay.
Yes.
Okay.
Yep. That's right. That's right. Right. And remember, those are not forces. That's just it's a stress traction, right? Okay. And that's the way and that's how we say that it's a tau XY. Now, if I had talked about at point C, all right. Now at point C, which is here, not up here, but here, same torque, that's going to produce a traction going up. Okay. And so that's actually the same shear stress, the 4.23 KSI, but it acts in a different direction. So let me just draw that. If we were to look at a differential cube at point C, right? Here we go. Here's a little cube of material at point C. Right here, this is the cut face, right? That's what's exposed by my cutting it. All right. That's the face of the CD, but the traction is acting up. So in this particular case, we would have the traction component due to that 1,500 pound-foot torque acting up. So this would be the 4.23 KSI. It's the same TC on J, but it acts in a different direction. And now it also gets its couple tractions drawn on the cube. So this is not a tau XY. This is a tau in the ZX plane. So this is a tau ZX. It's the same, it's the same TC on J, but since we're talking about a different point in the body, it actually manifests itself in a different component. Okay? And that's going to be one of the really important things to be able to do in this chapter. That's why I say, like when I was talking about the bullets, being able to visualize how the combined loading acts on a point is really the most important bit here. Okay? All right. So that's the torsional stress. Right. Fine. We got that. Okay. The next one that we covered was, in this case, bending, right? So what happens with the bending stress? All right. This 4,000 pound-foot bending stress. Okay. So let's do that now. I'll do that in blue, I guess, for whatever else it's worth, right? So the bending stress. All right. So it's a normal stress, and its value is MC on I. So the M is the 4,000 times 12 pound inches, right? C is still the outer, it's the distance from the neutral axis to point B. That's 1.5 inches. And I is the 3.19 inches to the fourth. So that's going to give me a stress of okay. That gives me a stress of 22.6 KSI. And as I mentioned, I think last class, bending stresses are always the one that seem to be worse because they act at those bending moment arms, right? And so here, yeah, this is much higher than the torsional stress. Okay, so that's the value. It's a normal stress. How does it act? Well, if you think about, again, if we're on this cross section, right, and here's B, this whole thing wants to bend down, right? It wants to bend down. So the normal stress wants to pull out from point B. It wants to push in down here at point D. So it wants to come out at point B, push in at point D, and then at C and A, those are 2 points on the neutral axis. There is no stress due to bending at the neutral axis, right? So it vanishes here. So at point B, we get a normal stress component in tension, all right? And so that's what's coming out here. So in this particular case, we would have a normal stress coming out here and here, and this would be the 22.6 KSI. Now at point B, right, this is point C. At point B, that is a normal stress in the X direction, okay? Excuse me. All right. At point C, it's on the neutral axis, so there is no bending stress, or it's zero, I guess I could say. And then if we were to look at point D, I'm going to draw a little cube at point D. All right. We get a compressive stress in that direction. It's going to be still a sigma X, and that is the 22.6 KSI. The shear stress at that is actually going to look a lot like what's at B, but it's going to be in the opposite direction. It's still a tau XY, but it's in the other direction, 4.23 KSI. So I didn't put a negative on it, but I put the arrows in the other direction, okay? Now, lastly, right, we have to do, let's find another color, let's do green, I guess. We have to do the shear stress, right? We get the shear stress, the transverse stress due to this shear force acting down. These are usually the smallest, right? And so we got the transverse shear. Oh, this is a weird pen. Okay, that's like taking way too much memory on my computer. Okay. Okay, so that is going to be the tau equals the VQ on IT. All right. And I always forget what that is for a circle, but in this particular case, right? Oh, what am I talking about? Okay, so in this particular case, right, here we are up at point B at the top. So remember, the transverse shear stress here vanishes. It goes away completely, okay? So at the top, at point B, this actually goes to zero. It also would go to zero at point D. Now at point A and point C, it's going to be max, and we'd compute Q over that half circle area, and that would be a shear stress that actually acts down. So if we were to put the VQ on I shear stress at point C, it would negatively combine with the same shear stress component, a tau ZX from the torsion, but it actually acts in the opposite direction. So it would subtract off of it, okay? Well, but anyway, so, originally we were just talking about a point B. So in fact, the transverse shear contributes nothing to point B. And so at point B, this would be our answer, okay? So that would be the answer. And very important in this chapter that when you do the answer, you don't just give me this number or this number. You need to be able to draw it on the differential cube. You need to be able to visualize it on that differential cube, okay? All right, okay. I am going to apologize because I have to actually attend a meeting, but it's on this other computer. So I will sort of bounce back and forth. I know that's kind of rude, but I will give you a problem to do now. It's going to be a little bit of a stretch problem. Well, actually, let me get started for you, okay? But the next problem I was going to do is 821. And in 821, oh, where it is, it's up here. I drew it up here. Well, that's 823. Okay, let's do 823. So I cut it, pasted it. So here they have this bent bracket, which two cables pull on it as shown, right? With a force of 1.5 thousand pounds, right? They want you to figure out the maximum normal stress in this bracket. Now, here's the trick. When you cut through here, okay, if we draw that free body diagram, I'll do it here to the left, right? We have the force here of P. So that means we have a tensile force of P acting at that cross section. But also because it's offset by the 4 inches, right? For this to be an equilibrium, right? The way this is drawn here, there's a moment kicking counterclockwise. So there needs to be a bending moment going the other way, and its value is going to be P times the 4 inches. That's the moment. So if we look at this, if we look over this cross section, right? So this is the cross section blown up, all right? We have this, the axial stress is just due to P. So they are going to be uniform over that face, normal stresses in the X direction. And their value is just going to be P over the cross-sectional area. So that's the stress, the normal stress in the X direction. We'll call this the X direction, okay? Now, superimposed on that are the bending stresses due to this moment, the 4 inches times P. Now, it's going to be compressive at the top and then become tensile at the bottom. And the stresses are going to look like this. And so this max value here is going to be MC on I, and this one is going to be minus MC on I. It's also a sigma X stress. Oops. All right, it's a normal stress. And at the top, one's going to be positive, one's going to be negative. So the bending stress is going to negatively contribute to that. So that means the biggest value is actually going to be at the bottom. So when you add these together, what you will very likely see on this cross section is stress that might look like this. The stress profile looks like this. Okay, so basically like a DC, sort of signal added on top of this linear signal, right? And so what they're asking you here is to find the normal stress, and the answer will be the contribution from both the P on A stress and the MC on I stress, and the maximum value, which is near the bottom, okay? So I'm going to break you into groups. I would like you to do problems 823 as well as 842. And if you have time, you can also do 843. It's basically the same thing as 842, just at a different point. Okay? I'm going to break you up into groups. All right. So, how do we do on problem 821? Were there any questions on that?
Yeah, I have a question, Professor. For
Sure.
for the problem, we consider the moment to be the moment to be equal to the force of the 1.5 kilopounds,
Mhm.
the 4 inches plus the radius of the tube. So it will
Oh,
equal.
okay. Yeah. Okay. Yeah. Yeah. You probably, you know what? Yeah, you're probably right. You probably should have done it. Yeah, that makes sense. Yeah. Yeah. I'm down with that. Yep. Yeah. Because the moment acts through the center of the, yeah, you're right. Does it, I don't know, which way does it draw? Does it draw to the bottom or to the center? I don't even remember.
It's to the bottom, yeah.
Oh, okay. Yeah. Then if it is to the bottom, then the moment should be the moment arm is 4.75 inches.
Okay, thank you, Professor.
Right. Yeah. Sorry about that. Right. Okay. So let me just show you what I did real quick, I guess. Just to visualize it, right? So, okay, so my moment's a little bit off, right? So, first we calculate the axial stress, the P on A stress. So it's 1.57 kips over the area, which is, I got 1.77 inches squared. So I got 6 KSI. And so that basically looks like this. And this is roughly to scale, okay? So you can see over the entire face, we have a uniform tensile stress there of 6.03 KSI, right? Then combined on top of it is the bending, right? Which, yeah, you're right. This should be 4.75. And if that's the case, wait, I must have done that wrong. I must have done that. Wait, 21. This comes out to be 21.5 KSI is what I get here. Okay. And what does that mean? That is, remember, it's not going to be uniform. So that's visualized here. Its magnitude is much greater than the P on A stress, the axial stress. And it is going to be compressive at the top and tensile at the bottom. So when you add those together, the 6.03 is going to be added to a negative 21.2 on the top, right? So if we look at it this way, at the top, we're going to have 6.03 minus 21.5, which is negative 15, right? So here we're going to be at negative 15 KSI. And on the bottom, the 6.03 adds on to the 21.
Professor,
Yes.
I run the stress of the actual stress because I got a different answer. Wouldn't it be 0.849 KSI instead of 6.03 KSI?
Oh yeah, 0. Okay, whatever. Well, don't yeah, fine. But let me just do the visualization and let you get on to the other stuff, right? Yeah. But okay, so the two add together, right? And then here you would get a positive 27.5. So stress state actually looks like this. All right. So in fact, what happens is the effective neutral axis has shifted up and the maximum stress is going to be down here at the bottom. It's not equal top and bottom, right? Because of the combined loading situation, okay? All right, let me let you guys bounce back and do the other problem, the 842. And that one is going to be more similar to the example that I did previously, except you have more components. So there's 3 forces acting on the bevel gear. My recommendation is to go over with each one of those forces individually, okay? And I think you'll find it to be almost identical to the first problem.